Alright, so we're in the halfway point for our general chemistry module. So for the 7th lecture, we're going to talk about thermochemistry. Starting first with systems and processes. A system can be classified as isolated, closed, or open, depending on matter and energy exchange. Isolated systems, as the name would suggest, is where matter and energy are not exchanged with the environment, so it's completely blocked off from its environment. Closed, on the other hand, can exchange energy but not matter, and open is where both can be exchanged. To note, a closed system, for example, would be something like a sealed cup. It's technically not exchanging the matter within the cup with the environment, but the heat is dissipating from this cup. An open would be if I were to take the lid off of this cup. Now, the vapors from the fluid inside the hot water are leaving the system, along with energy. It's very difficult to get an isolated system, and truth be told, they're not very common because it's very hard to prevent energy and matter transfer. The second portion of our little fundamental slide is processes, and there are several that we do need to know. An isothermal process is one where the temperature is constant. An adiabatic is where there's no heat exchange with the environment, isobaric being a constant pressure, and isovolumetric being a constant volume. Isochoric is another example of an isovolumetric system. Therefore, we need to mention that here. Make sure you know how to read these expansion graphs, which are listed as pressure volume graphs. A pressure volume graph is going to look something like this. Depending on what type of process it is, it's going to dictate how this is going to look. Let's do an example. For an isobaric graph, there's a constant pressure. So what are we going to note with this process? Well, pressure is constant, so it's simply going to proceed like so. An adiabatic one is where there's no heat exchange with the environment. And an isothermal is going to be similar as well. So you'll probably see something that looks like that. An isovolumetric graph is where the volume is constant. Now, how do you think this would look? Well, the volume is constant, so you're actually going to see something that looks like this because the volume doesn't change. So you're usually not going to be tested on these isovolumetric graphs. Make sure you know how to read these graphs, and make sure you know what it entails. For a lot of these, just the name will give away what it is. Iso, isolated. Thermal, therm is temperature. Bar is pressure, for example, barometer. And isovolume, which obviously is volume. So in a lot of ways, the name for most of these is going to give it away. The only one that you're going to have to generally keep track of is adiabatic. We have to talk about the laws of thermodynamics if we are going to have a proper discussion of thermochemistry. We will go into the first law, but before we can go into the first law, we do have to state the 0th law. The 0th law of thermodynamics is very simple. It states that if a system is in thermodynamic equilibrium with another system, and that other system is in thermodynamic equilibrium with a different system, then all systems are thermodynamically in equilibrium. So, if we were to have a quick recap of that, it simply would state that if A is to B and B is to C, then A has to also be to C. So it's a transitive property, but it's important because it's a foundation for the other laws to stand on. With that discussed, let's go into the first law of thermodynamics. This simply states that energy cannot be created or destroyed. So the change in potential has to be Q minus W. What is Q and what is W? Well, U is the internal energy of the system, Q is the heat added, and W is the work done. It simply states that you can't create or destroy energy, and by that facet, matter, because if we remember from our physics module, matter is energy. You can thank Einstein for discovering that one with his equation E equals mc squared. Because of this generality, the first law of thermodynamics is commonly called the law of conservation of matter and energy. After going into the first law, let's go into states and state functions. A state function is basically a description of the physical properties of an equilibrium state. And these are path independent. What does it mean to be path independent? Well, when we're talking about something like a phase diagram, no matter how we get from one point to another, it's going to be the same. That's going to be a state function. Standard conditions for most thermodynamic systems is listed at the bottom, at 298 Kelvin, 1 atmosphere, and 1 molar. Take note that this is, quote, room temperature or room conditions. Standard temperature and pressure, STP, is something entirely different, so make sure you keep those two separate. The standard state is the most prevalent form of an element at standard conditions. So when you're running calculations, most of the values provided to you will be in standard condition. What constitutes a phase change? Well, to look at a phase change, we have to look at a phase diagram. And there's a couple points we have to mention. There's fusion and freezing, and these are the boundaries between solid and liquid. So fusion is when it goes from solid to liquid, and freezing is the other way. Vaporization and condensation occur at the boundary between liquid and gas. So vaporizing is when liquid goes to gas, and condensation is the opposite. The interesting one is sublimation and deposition. This is between solid and gas. So when a solid goes to a gas, it sublimes, and when a gas becomes a solid, it deposits. This isn't as common as the first ones we've mentioned. The critical point is where the liquid and gas phase are completely indistinguishable. And the triple point is where all three phases coexist. So how about we draw a simple phase diagram at the bottom to illustrate this point. So when you look at a phase diagram, it's going to look something like this. So this is going to be pressure and temperature, and we're going to have a system like so. So if we were to say that this side is solid, this side is gaseous, and this side is a liquid, we have our graph. So the critical point would be listed here. Any temperature beyond this point is going to be indistinguishable as a liquid or gas. The triple point will be listed here. Now, as we talked about, this boundary right here is where sublimation and deposition occurs, the boundary between solid and gas. Solid to liquid, right at this point, is where fusion and freezing are going to occur. And the boundary here, liquid to gas, is where vaporization and condensation are going to occur. Make sure you know how to read these graphs, and take note that the position in which solid, liquid, and gas are going to exist at is going to be different for each compound. What is heat? Make sure that you know that heat and temperature are not the same thing. Temperature refers to the average kinetic energy within a substance, whereas heat is the transfer of energy that results from a difference in said temperature. Although in our daily language we use these terms interchangeably, when we're talking about them in terms of chemistry, they're two very distinct concepts. When we're talking about how heat will be tested on the MCAT, we have to talk about calorimetry, which is quite simply heat transfer. When there is no phase change, we can simply use Q equals mc delta T, or heat absorbed equals m mass, C specific heat, and delta T change in temperature. This can be in Celsius or Kelvin, take note of that. A very easy way to remember this is Q equals MCAT. Why? Because you're going to see this on your MCAT. If there is a phase change, we have to use Q equals ML. And that equation, quite simply, is the same. It's heat absorbed equals mass times L. Now, what does L mean as a quantity? L is simply the latent heat of a substance. If we were to measure the heat transfer going from one phase to another, we would have to calculate the heat transfer from one stage of one phase, then calculate the phase change, and then calculate the subsequent heat transfer after the said phase change. So if I went from liquid to gas, for example, I would have to calculate the heat transfer from the liquid phase using Q equals MCAT, calculate the phase change using Q equals ML, and then calculate the remaining heat using Q equals MCAT when we're in the gaseous phase. Make sure you take note of this. If you don't account for phase changes during your calculations, you will get incorrect answers, and the test will try to trick you on this by having answers if you calculated without said phase change. What is enthalpy? Enthalpy, abbreviated as H, is a state function where we calculate systems that have undergone a process. And enthalpy is additive. So the enthalpy of a reaction, change in enthalpy of a reaction, is quite simply enthalpy of the products minus enthalpy of the reactions. If delta H is greater than 0, it's considered endothermic, meaning that it took energy in. So there's more energy in the products, or more enthalpy in the products than in the reactants. However, if delta H is less than 0, that's an exothermic process. Why is that? It's because if you think about it from a mathematical standpoint, that means that there was more enthalpy in the reactants than the products. Therefore, we lost some along the way, meaning that energy was kicked out of the system. As I mentioned earlier, enthalpy is additive. Therefore, we can simply use the sum of each individual step if we're looking at more complex reactions. That's where Hess's law comes in. It simply states that total potential energy is the sum of each individual step. And if you remember when we look at the enthalpy of a reaction, the delta H, bond enthalpy actually operates on a very similar principle. It's simply the bonds broken minus the bonds formed. What does that mean? It's effectively the total energy absorbed minus the total energy released, which makes sense considering our previous slide. So we've covered enthalpy. Now let's go into entropy. Now, we do need to be careful when we're talking about entropy because entropy is commonly thought of as disorder. However, it's the ratio of heat transferred per mole per unit K. So it's a measure of how energy spreads out, how energy is spread throughout a system, and it's maximized at equilibrium, which would make sense. When a system is at equilibrium, it's at the highest state of entropy, meaning it's, quote, as happy as it can be. Be careful when you mention entropy as disorder. Although it is usually called disorder, it's more of an expression of energy than anything. The equation for entropy is listed below, but you won't really have to do these sorts of calculations on the MCAT. It's going to be more important that you understand conceptually what entropy is. It simply states that energy is going to spontaneously disperse over time, which is listed below. It simply states that the change in entropy in the universe is always going to be greater than 0. When you look at the entropy of the reactions, similar to delta H, delta S is also going to be just the products minus the reactants. This brings us to the second law of thermodynamics, which is commonly called the law of entropy. It simply states that energy is going to spontaneously disperse over time. And below we have the equations on the previous slide. When we have a discussion of thermodynamics, and the second law in particular, we do have to take into consideration entropy, just as much as enthalpy when we're running our calculations. If you remember our discussion of equilibrium in the previous lecture, entropy and enthalpy play huge roles in how systems reach equilibrium. Think of thermodynamics as mathematical representations of systems' desire to reach equilibrium. Now that we have had our discussion of enthalpy and entropy, this brings us to Gibbs free energy, which is arguably the most important concept in the entire MCAT Gen Chem unit. The equation is listed as delta G equals delta H minus T delta S. How I generally remember this equation is goldfish are horrible without tartar sauce. So, goldfish are horrible without tartar sauce. Simply stated, delta G equals delta H minus T delta S. Gibbs free energy is simply a measure of spontaneity. If delta G is less than 0, the reaction is stated to be spontaneous. If delta G equals 0, the reaction is at equilibrium, and if delta G is greater than 0, the reaction is non-spontaneous. Let's take a look at how delta H and delta S play a role. If we were to look at our values of delta H and delta S, so I'll put a little chart right here, so delta H and delta S. There are different scenarios. What if they're both positive? Well, if you look at it just from a math standpoint, if delta H is positive and delta S is positive, it's only going to be spontaneous at high temperatures. What if delta H is positive and delta S is negative? Well, if you think about it, a negative times a negative is always going to be positive, so there's no way that delta G is going to be less than 0. Therefore, this is going to be non-spontaneous at all temperatures. What if it's the opposite? What if delta H is negative and delta S is positive? Well, if you look at it again from a mathematical standpoint, there is no way that we can get a delta G that is not negative. Therefore, it's spontaneous at all temperatures. And lastly, if they're both negative, then it's going to be spontaneous at low temperatures. The two that we have to look at is if they're both positive or both negative. they're both positive, it's going to be spontaneous at high temperatures. If they're both negative, it's going to be spontaneous at low temperatures. Whereas if one's positive and one's negative, like these two middle cases, you're going to have non-spontaneity or spontaneity at all temperatures. Make sure you're aware of this when you're studying for the MCAT. The standard Gibbs free energy, as you would probably suggest, is also additive. Simply stated that the delta G of the reaction is simply the sum of the products minus the reactants. This is true for entropy and enthalpy as well. So you can save yourself some time when you're memorizing these equations if you simply remember that enthalpy, entropy, and Gibbs are all additive. There's a few other Gibbs expressions that we do have to mention before we conclude our lecture. Using the equilibrium constant, we can simply state that the delta G naught of reaction is equal to negative RT ln K. Simply state it's the R constant times the temperature times the natural log of the K constant, the equilibrium constant. If we were to use the reaction quotient, we would have it listed below. Now remember, reaction quotient is simply a snapshot or a moment in time of a reaction. It does not necessarily state that it's at equilibrium. So we'll finish our discussion there, but at the end of the lecture, we did mention Gibbs expressions. I would strongly encourage you to have these memorized when you go into your testing. Please join us in the next lecture as we go into certain phases, starting first with the gas phase.